I want to introduce the concept of a power series and see how this relates to what we've studied so far regarding series. So we're going to define a power series centered at x equals a to be a series of the form given here where we start the sum at k equals 0 up to infinity with terms c sub k times x minus a raised to the k. Now here, a couple things. We refer to c sub k as the coefficient. So this could just be a scalar that has no dependence on k, but it might depend on k, we're seeing here. But in particular, there are no x's involved in that. We have a single x minus a term raised to the index k. And so one of the things we'll also note here is that a power series is going to be something that has these integer, non-negative integer values on the exponent there for x minus some value of a. And a, as kind of referenced in the definition here, we call that the center of the power series. So you can imagine there are lots of different power series by choosing different values of a and different coefficients c sub k. And the traditional way we're expressing this here is starting this at k equals 0. However, you might see power series expressed in this way where k starts at, say, 1 or 3 or 100. That's still of this form because the missing terms, you could imagine, are simply terms with coefficient 0. So to see some specific examples, one of the things I'd like to do here is identify some of these pieces for our specific examples. So what I have here, first of all, this is a power series. And when I'm thinking about what the center is and what the coefficient is as well, notice here that my center, let's choose a different color, my center is 0. The reason is that we could express x to the k as x minus 0 to the k. The coefficient then is what we're multiplying the x minus 0 to the k by, and that's going to be, in this case, 1 over k factorial. In my next example, this again is an example of a power series. Here I can see a little bit more readily that the center is kind of explicitly written here, but one of the things we have to pay careful attention to is we should expect to see x minus the center. Well, I can rewrite that as x minus negative 2, and so I see that the center is actually negative 2. And again, the coefficient is what's being multiplied by that term, and so we get that 2k factorial represents the coefficient. And sometimes we might have to do a little work to identify both the center and the coefficient. And I'm given this one here, and there's this unexpected 2 coefficient in front of x. So as it's written, it's not immediately clear how this relates to our definition. In order to see the relationship there, we can simplify what we have. So first of all, observe that 2x minus 4, we could write that as 2 times the quantity x minus 4. Times the quantity x minus 2. And so in this instance, if I wanted to write this so that I had an x minus a to the k, what I could do is pull that 2 to the k out front. So the numerator I'm expressing instead is 2 to the k times x minus 2 raised to the k. And my denominator is k plus 1 squared. And now by simply rewriting it in that way, I can see that my value of a, the center, is positive 2 because it's x minus 2. And the coefficient actually is 2 to the k over k plus 1 squared. Notice that the 2 to the k is not immediately obvious in the original way the power series is presented, but that actually is part of my coefficient if I'm hoping to put it into this form. Now, one consistent thing you can notice for all of these is, yes, we can find the center by strategically rewriting the terms in a way to make it very clear what x minus a to the k would be. But the other thing to notice is that you can quickly find the center by trying to figure out what value of x you could plug in that would make the terms vanish. In my first example, if I plug in 0, I'm going to have 0 to the k. That would make the terms vanish. In my second example, if I were to plug in x equals negative 2, again, we would have that 0 to the k. And then finally, this 2x minus 4, we know that that's 0 when x is equal to 2. So that's kind of a quick way to find the center of your power series. And then the last thing I'd like to mention in this video is the connection to series that we've seen before. A big difference here is this presence of x. And when we talked about convergence test for series, we didn't have this unknown variable x in there. But think about how if I were to take one of these series and plug in a value of x, then I would get something that should be hopefully familiar. So for instance, for this last one, we can plug in different values of x. So if I were to plug in x equals 0, then I would get the series 2 to the k times minus 2 to the k over k plus 1 squared. And of course, I could write that top part as negative 4 to the k. If I were going to plug in, let's say 3, well, in that case, the resulting series would be 2 to the k times 1 to the k, or 1, over k plus 1 squared. So essentially, each time I plug in a new value of x to my power series, I get this different series. And you can imagine that there are infinitely many choices of x that we could plug in there. And now we want to consider the question of, for each of those new series, trying to test to see if it converges or diverges. Now, at face value, that sounds like a very complicated problem. I have infinitely many series, and I want to determine convergence or divergence in each case. What's great about power series is that if we don't plug in x, but leave that x value in there, perhaps we can look at this from a broader view and try to determine in one step what values of x would lead us to a converging series and which ones would lead us to a diverging series. Notice the beauty of that is that hopefully by a little bit of work, we're able to get a statement about infinitely many series at once. So this leads to the notion of when does a power series converge, which we're going to discuss in another video.